now, yeah, we have one of our research paper talks, DeepBench, benchmarking JSON document stores. The work is done by SAP. So Stefano, you can yeah, take the stage.
Yes, thank you. Can you hear me?
Yes,
yes,
I can.
Okay. Yes, I'm Stefano from SAP, and first of all, thank you for having me. And I'm going to present the work. So Daniel Ritter, Marco Schröder, Nils Rörup, and myself made on benchmarking JSON document store. So first of all, I would like to start with, let's say, not really a scientific diagram. It's the plot that comes from Google Trends, and it summarizes the searches over the last decade of few of the most common exchange and storage formats. And we can see that there is a trend for JSON, and it became more and more popular as a search item. And we might conclude that it became more and more popular also its use. And so we can actually confirm this, that the trend is really like this with two facts. One is the popularity of JSON document stores and database like CouchDB, MongoDB, OrangeDB increased rapidly. And on the other side, even traditional relational database vendors started investing in JSON support or extension. An example is Postgres. So I think everybody is familiar what a JSON document is. So JSON document is JavaScript object notation and is a text-based language independent data interchange format. In the slide, you can see a document that is used to make a payment during a SEPA credit transfer, and it is a JSON version of XML file. And we can see, so here are more or less all the characteristics of a JSON document represented. So we might have we have this self-similarity structure, so objects can contain other objects and many data types. So we have a string, an array of objects, and so on, or so numbers, floating point number, and so on. Clearly, when we store such data in a database or in a database which has no constraint on the schema, we would like then to query back the database to have the data back. And many vendors develop different ways to query JSON data type. In this example, we use SQL with this specific path expression. So to access an element inside the JSON, we can just navigate from the root downwards in the depth of the document, following just the identifiers, and we can arrive at the wanted element. Clearly, there might be more complex things that we can do. For example, we might want to work with the array and use a special operation, that is the unnest operation. In this case, we have the filter, which navigates through the object, and then we have the array, which is properly unanalyzed, so unnested. And then we can also, on top of this, create an aggregation function. For example, we might want to aggregate over all the value, the IMT value, and produce the average of these things. So when dealing with the benchmarking, the scale dimensions are really important, and most of the current benchmarking actually have take care to consider many of the scales. So the one of the first one that can come to mind is concurrent users. Then we have a result size, and then we have specific dimension that have to do, query complexity, and then we have specific dimension, for example, JSON specific dimension, because the structure of the document is quite different from a table, and so on. So there are many more dimensions. So in the next slide, I would mostly like to explain more in details what actually are those dimensions. So on the bottom right, we have the result sets, which actually is one dimension that contains much more possibilities. So we might have the result set, so the number of rows in the table, let's say, that we receive back. Then we might have the number of rejection that we made that increase or decrease the number of columns. And then inside each cells of the table, we might vary the result size, the type, and so on. Next to it, on the left, we see a document, and there are the two main dimension. So the nesting dimension, like objects inside other objects, and the second dimension is an horizontal dimension. So we have an array, and the array can be indefinitely large. So we have no restriction on the type of the data type and of the elements, and also the number of elements. And this actually is something that in most common database is most common benchmarking is not fully testable, because there's a lack in supporting this feature. And on the top right, we finish the circle of the dimension. We see a select statement, so a query. And the query actually is the link between the data and let's say the result sets. And we have a lot of variables. So we have a possibility to project different keys, produce different predicate, and so on. So is this, it will give just so the domains, and so so the challenges when developing JSON documents to benchmarking actually is that current benchmarking practices focus mostly on YCSP, which is a key value benchmark. So it's an object like, so it contains object like documents, but it only focuses on the first access, so the access on the first key. So there's no nesting, and also TPCC, it was transformed into to be able to use with MongoDB, but also lack in this dimension. So there was actually recently advance in generating JSON data in like Wisconsin's benchmarking, and also UniBench, but actually there is really this lack in the require for objects, array, and data, and query and workload dimension, and to link the two things together to allow workloads that are not so explored and so on. So what we did actually was to define a scalable JSON document store benchmarking with configurable custom workloads guided by query and data generation. So what I mean with this part, so which is actually the main part, is that we concentrate on data generation on one side and query generation on the other. And with the help of the configuration file, we can generate arbitrary flexible data. But the main thing is that we use this configuration file so that the query generator actually take care of to use the structure of the data and generate consistent queries. So take into account data types. For example, if an array is present or nested element might be accessed, take into account constraints on value allowed in the data, and try to produce proper filter, proper aggregation function, the use of indexes on specific elements. And all this is done using a feature matrix dedicated. So there are general things that are supported by all database, but if that specific database has some specific functionality, then we can just feed the query generator to produce new queries. The thing is nice because we can produce automatically new queries and just run the benchmark and for days maybe and look at the results afterwards. We implement then a fully functional DeepBench prototype, and we try across different systems. And then we conduct an experimental evaluation of several state-of-the-art document store with DeepBench, resulted to, so we found some interesting insight that could not be found before, basically because there was no benchmark allowing for this deep search. So in the use of this self-similarity of JSON data type. So now briefly I will present some of the experiments. So as a setup, we use as the databases. So MongoDB, the version is given, and it will be in the diagrams MDB called, and then PostgreSQL in its JSON extension. So, and it will be PQJ. We use a machine with 120 cores and 500 gigabyte of DRAM. And DeepBench's prototype is in Python, and we made so basically two classes of experiments. So nesting object, which is not shown in this presentation, but is in the paper, array, and then we make an experiment to use existing OLAP benchmarking, the BI benchmark, and just take the raw data and feed to our benchmarking and produce the results. So first of all, since the one of the experiment has to do with unnesting, so unnest actually is a SQL function that return a result table with one row for each element of an array. So it's like the transposition in normal linear algebra. The things are a bit more complex when we have arrays of arrays. So when we do two sequential unnests, so in this case we unnest first B and then unnest the results, the array present in A, and in this case we just follow one path and we open like a fan the arrays that we encounter on the way. There is another possibility to unnest. It's like unnesting independent arrays where there is no common root, and there is a Cartesian product of the results, but it's not. So in this experiment we didn't do that. So just for annotation, because this unnest is the SQL function, but Postgres actually use a special function, which is JSON BRA elements, and MongoDB has the function is called unwind. So first of all, the query I will present now, the two queries. So we have a query for Postgres, a query for MongoDB, and we see that, let's say, for example, the query from MongoDB is easier in these slides to read. So we unwind the first level, then we unwind the second level, and then we do a match on the results of the last unnesting, and then we project just the result back to the user. The data were so generated that we return around 500 results from the query. So what actually means from the database perspective when it wants to run this query, it means that you have to navigate to A1 and then traverse the arrays. So I have to navigate through the array, so look and search the first element. And then since we want to re-unnest the element inside these documents, we will then jump into A1 and navigate through the second array and so unnest. So we can see that it's really expensive operation. So here are some, so the results. Fit actually it's more like a trend. It's not really a fitting because there are few, not so many data points. But we can see on the x-axis, there are the number of sequential unnests that were performed, and on the y-axis, we have the runtime in seconds. And we can see that really with the time, with the depth of the unnesting grows, there is really a significant degradation in performance. However, from the two systems, we can see that Postgres is more stable. It might be because better memory management, but more investigation is needed. While MongoDB is really performant at the beginning, but when the user arrives at like 6,400 user, then it starts degrading a bit more. We tested against also an anonymous system with some optimization, which is a document store under the with clause, so it's an anonymous system. And we see actually that there is really improvement in this kind of query. So with this really easy, let's say, optimization, we try to avoid this expensive operation as much as possible. We can see that actually the improvement is really big. However, as the number of sequential unnest increase, then the performance of all the system agrees on. So this more or less. So we have a nesting, deeply nested array is really complex problem as we show, and optimization actually are possible. Maybe they were not explored because also lacking of such benchmarking available. The second example actually is about OLAP query, and we took the workbook food from the BI benchmark, and what we did, we just take the CVS file and convert it into a JSON document. And afterwards, we took the query from the original workbook and we translated it. So this is automatically done, translated it into the Postgres specific dialect to deal with nest, so with JSON data. And afterwards, we run also this data generation to produce other data. For example, automatically generated some average. So identify that there is the possibility to perform an average on the value total bytes because it's a numeric value. And then it also noticed that there are not so many integer value for activity in second, and so put a predicate on this data. So again, we have some performance shown in the diagram, and also again is relative to system X. And we can see also here, so here we have on the left diagram, we have a query without index with group by and order by. in the middle, we have an average done with indexes. So we use the index on activity second, which was automatically generated. And then on the right-hand side, we perform the same query without the index. Here, what's important actually is to see that there is improvement potential inside for this kind of workload. So as said, there is performance improvement and also improvements like indexing, analytical processing technique from column store, for example, might be beneficial also for document store. So I will now wrap up. So this work actually addressed an important shortcoming in document store benchmarking. So as underlined, there is work that has been done, and so maybe this gap will be closed also from other researchers. But so we saw this lack in JSON-specific data in query generation, and we went along this path. So DeepBench is so in extensible, scalable. So extensible also because we might just add a new system with a few lines of code, and scalable, and is a JSON-specific benchmark. And so, and then for the first time, it was possible to gain deeper insight into strengths, weaknesses of this system in this, let's say, corner case where we explore this to depth of arrays and objects. And with this, so in future work, we plan to further investigate and identify actually these weaknesses, explore solution, and to see to see this benchmark in action as a tool to identify weaknesses and look for possible improvements. And with this, I would like to thank you for your attention. And if you have any question, please ask them.
Yeah, thanks, Stefano, for the talk. I don't currently see any questions on Slack or any hands raised here. Any questions in the room?
Yes.
Yeah, great.
Hi, thanks for your talk. To what extent does your benchmark incorporate or generate data of varying structure and incorporate effects such as missing data and things like that?
So, so maybe I didn't. And so, what do you mean with the missing data?
Sometimes in JSON documents, you may have the case that one document in your collection like has the path ABC and another document does not have any object AB at all.
Yes. So the thing is that so we have a configuration file where we say which are the false paths. So we guarantee that some paths are present in every document, and then we guarantee also that some values are present in the number of values. And then there is a part of the generation that is actually so arbitrary. So it can be everything. And maybe this might be a problem. But so we generated the query then according to this known path and known constraint on the values, data type. So in this respect, but it might it might also be possible to extend and to allow to have document without fields, but actually most of this database just so if you say please I want the document where A is 1 and there's no A, it will just pass to the next document. So I don't know if I answered your question, but
I guess. Thank you.
So it's more to say that we don't cover directly this thing. So, but So we more focus on getting some kind of structure and then producing query that look into the data and query the data properly, not just generating random query to find bugs like in this fuzzer as Mark was talking before. We're more concerned on query that have some meaning.
Hi, this is Steffi Scherzinger from the University of Passau. Thank you for the talk. It's a topic I'm really interested in. So I have two questions. First of all, it looks a bit like a micro benchmark to me, where you're specifically targeting deep nesting. And my first question is that a problem that you encounter, these kinds of queries that go for deeply nested data? And my second question is, do you have plans to integrate your benchmark with an existing benchmark harness, such as YCSB or Benchbase, so that people don't yet have to install yet another benchmark harness, but could use something that's already there and then easily plug in your benchmark?
Okay, yes. So for the second part, so at the moment it's not open source. So and we don't know if it will be open source. So the question, so it depends on these things. But I guess if it becomes open source, then it's a good way to go to integrate in some existing thing. And so and
first part was about the deeply nested.
Yes, so and the main reason is that the JSON document has this characteristic of deeply nesting of objects. So I didn't show in the slides, but we have some. So maybe I can go and we then look at access of just access of deeply objects. And so let's say we jump from one to the other without any other operation, and the things was just to find out actually how the access itself. So which is the weight of the access of internal elements in the query, and but so these are data structures that are found really easily. So data lakes nowadays stores a lot of document just as JSON, and they might be really complicated data structure. Arrays actually also nested arrays can be so when gathering data from sensor or time series, there are things that so that they are quite common things. So that was the reason to go in the direction to look for these deeply things. So this nesting. But so if I hope I answered your question, because maybe you meant something else.
No, was the answer.
Okay, thanks.
So I don't see any more questions in the room. Do we have something online?
No, I don't see it either, but we are also, I think, roughly on time in terms of the Q&A time as well. So we can end the session. Thanks a lot, Stefano, for your talk once again.
And thank you.